Estimate the sum of the first 10 terms to approximate the sum of the series at n go from 1 to infinity of 1 over n to the fourth plus 1. Then estimate the error involved in this approximation. This series looks like the p-series 1 over n to the fourth, where p equals 4, which is more than 1, so this series is convergent. But this is not good enough. We still need to show the inequality. We see that n to the fourth plus 1 is greater than n to the fourth. Therefore, 1 over n to the fourth plus 1 is less than 1 over n to the fourth power. Since the series 1 over n to the fourth converges because it is a p-series conversion, and 1 over n to the fourth plus 1 is less than 1 over n to the fourth, we conclude that the series 1 over n to the fourth plus 1 also converges because it is the smaller of the convergent series by the direct comparison test. Now that we know the series converges, we can approximate the sum. Using the first n terms only, n go from 1 to 10, 1 to 10 terms, 1 over n to the fourth plus 1, we approximate using a calculator that this is 0.57819, and this will approximate the sum of this convergent series. If we were to estimate the sum of 1 over n to the fourth only, then from the integral test we see that the remainder t sub n is less than or equal to the integral from n to infinity of 1 over x to the fourth dx, and evaluate this, we will see that this is 1 over 3n cubed. But this is the series at n go from 1 to infinity of 1 over n to the fourth plus 1. We know that 1 over n to the fourth plus 1 is less than 1 over n to the fourth. The remainder of the given series is therefore less than the remainder of the series 1 over n to the fourth. We conclude that r sub n, which is the remainder of the given series, is less than the remainder of the series 1 over n to the fourth. But t sub n is approximately less than or equal to 1 over 3n cubed. In this case, n is 10 because we're using the first 10 terms. We find that r sub n is less than or equals to 1 over 3 times n is 10 now. This is approximately 0.000333, and this is the error involved in the approximation. What we are doing in this case is that we compare two series. We have the convergent series, and given another series whose terms is less than the convergent series, we see that this smaller series is also convergent. The remainder of the given series is r sub n, and the remainder of the simple series that we use to compare to is t sub n. We see that r sub n is less than or equal to t sub n. R sub n, which is the remainder, might not be evaluated easily, but t sub n is the remainder of a simpler series, and that is usually the case. When we compare a given series with another series, we either use a p-series or a geometric series to compare these two. And we can easily find the remainder of the p-series using the integral test or the geometric series using the geometric sum.